Today we shall discuss about a theorem on flow networks, namely the max flow min cut theorem, which states that the maximum flow of a flow network is the value of the maximum capacity of a min cut. So, we need to first define what is a min cut and what is its capacity. Then after that we shall state and prove the max flow min cut theorem. And before we see what is a cut and what is min cut, we can recollect the basic things that we discussed about flow networks. The agenda for this lecture is this theorem, and first let us recollect the basic aspects about a flow network that we discussed in the last few lectures. Here is a flow network given with a flow F, and in a flow network there is a source vertex which produces materials to be transported and which is assumed to have enough capacity to produce any amount of materials that the network can transport, and the materials are transported from the source to a destination called sink, and the materials are flowing through this medium called conduits connecting two vertices. And a conduit is characterized by its capacity, in this example 20, which is the maximum rate at which materials can flow along that conduit, and then it is also characterized by the flow through that conduit, which is the actual amount of materials passing through that. And given this, in this particular case, note that the capacity is 20 units and you are sending only 15 units of materials along that. So, there is a remaining or residual capacity of 5 units. We also have seen what is the net value of this flow, which is the net outflow from the source vertex, that is the total outflow from the source minus total inflow to the source. Here inflow is 0, so it is 11 plus 8, 19. We also have learned about residual networks. Given a flow network and a flow, it induces a residual network based on which the Ford Fulkerson method obtained an augmenting path if there, and then utilized it to increase the flow in the original network using flow augmentation. Now, here is in this given residual network, for this there is an augmenting path. Recall that an augmenting path is a simple source to sink path in the residual network, and the capacity of that augmenting path is 4, because in the middle the conduit allows only maximum of 4 units. So, this is a flow along the augmenting path, and if you look at only that flow, this is it. That is a flow Fp induced by this path. And now you can augment this flow along this augmenting path with the original flow in the network. So, you are getting this. How are you getting? If you look at the first flow along the same direction, you have 8 in the existing network and now 4 is added through the augmenting path. So, it is 8 plus 4. In the next conduit, you can see that it is in the opposite direction as that of the flow happening in the original network. So, you are subtracting, and in the third conduit you are having it on the same direction. So, you are adding 15 plus 4, and we also have seen that if you augment FP with F, the resulting value of the flow is the sum of the existing flow plus the net value of the augmenting flow. And we also have seen that when you augment, what you are getting as the result, the value is greater than the original flow, because we know that the minimum capacity of an augmenting path will be 1. So, these are all things that we know till now. Now, with that information, let us try to understand what are cuts in a flow network. An ST cut, it is called ST cut of a flow network, is actually a partition of the vertex set into two disjoint subsets S and T. So, these are the names of the subset to which you are partitioning the vertex set V. Partition means disjoint. And how are you partitioning? Such that the source vertex must be in the first set and the sink vertex must be in the second set. Example, given this flow network, this is an ST cut where all these shaded nodes are in the set S and other vertices are in the set T. They are disjoint. This is an example cut. You may cut here as well. The only requirement is that there is no common vertices for these two sets, and the source must be in the first vertex set and the sink must be in the second vertex set. So, both must be non-empty, because source, at least the source or sink is in SOT. I hope you are getting. The net flow represented as F of ST across an ST cut, for example, here is defined as, that is the net flow across, which is basically defined as the flow across this cut in the left to right direction. That is what I am saying here. If you look at all the flows going from left to right from the set S to this set T, you are taking the sum minus flows coming in the opposite direction. That is, flows which are going, total of the flows which are going from left to right minus total of the flows which are coming from right to left. For example, here there are two flows going from left to right with values 12 and 11, and one flow is coming in the opposite direction with value 4. So, the net flow across the cut is 12 plus 11, 23 minus 4, which is 19. Now, there is another factor for a cut, which is the capacity of an ST cut, which is defined as CST. This should be C, sorry for that. It is defined as the total capacity of all the conduits going from left to right. There we are not considering the reverse edges. Okay, this edge is not considered. Only those edges which are going from the set S to the set T contribute towards the capacity of the cut. So, just take the sum of capacities. So, in this case it will be 12 plus 40, because these are the only two contours going from left to right. Just add the capacities, you will get the total capacity as 26. Okay, what we discussed now is an ST cut is a partition of the vertex set into two disjoint subset S and T such that the source vertex is in the first set and the sink vertex is in the second set, and also the sets are disjoint. That is an ST cut. And why the name ST? Because the source is going to the first set and T, the sink, is going to the second. Now there is what is called the flow across the cut, which is the net flow. You take the sum of the flows crossing the cut from left to right minus the sum of the flows crossing the cut from right to left. In this particular example, 12 plus 11 minus 4. Now capacity of an ST cut, which is the capacity of all the contours crossing the cut from left to right or from S to T. T to S contours are not taken for defining the capacity. Why? We can see later. And there is a typing mistake. I should say this as CST, the capacity of the ST cut. Now we can have a lemma and a useful corollary for this lemma. What is the lemma saying? Let F be a flow in a flow network with the source S and sink T, and ST be any cut of G. ST cut is an arbitrary cut, any cut for that purpose. Then the flow across the ST cut, which is represented as f of ST, must be same as the value of the given flow. So, given a flow network and a flow, and if you look at any ST cut, then the value of the flow must be the net flow across the cut. The proof is not very difficult, it is left as an exercise, but we can verify in the example. Here we have an ST cut, a flow network and a flow, and the value of the flow is 11 plus 8, which is 19, and you can verify that 19 is also the net flow across the cut. So, 19 is the flow value, which is same as the net flow across the cut, that is 12 plus 11 minus 4, and which is nothing but the net flow across the cut. This is what the lemma is claiming. Assuming that the proof is done, we can proceed to see a corollary for this lemma, which is very useful for us. It tells that the value of any flow F in a flow network G is bounded from above, upper bounded, by the capacity of any ST cut in G. That means, given a flow network and a flow, its value must be upper bounded by the capacity of any ST cut. It does not matter what cut it is. If it is a cut, then its capacity is an upper bound on the maximum flow value. And it is a corollary of this theorem because, this lemma, because the lemma says that the maximum flow across the cut, the net flow across the cut is same as the given flow value. And what can be the maximum flow across the cut? It is upper bounded by the capacity of the cut. I hope you remember from the previous slide, otherwise please go back. Here the lemma says the value of the flow is same as the flow across the cut. Then what can be the maximum flow? The maximum flow across the cut, which is upper bounded by the capacity of the cut, and that is how the corollary follows. And the proof is given as a homework exercise, which is nothing but what we have discussed. You can do it very formally. now coming to the max flow min cut theorem, which says that if a flow in a flow network with source S and sink T, then the following conditions are equivalent. We are going to have three conditions where they are equivalent, is what this theorem claims. The first condition, the given flow is maximum flow value, is having the maximum possible value. That is the first statement. Second statement, for that flow and the flow network, the residual network contains no augmenting path. That is the second statement or condition. The third one, the value of the flow is the capacity for an ST cut in G. So, the theorem says these three statements are equivalent. It is equivalent to say F is maximum, the flow is the max flow, or saying that there is no augmenting path in the residual network. These two are easy to see because we know from the previous lecture. And the last one is interesting. Here it says that if the flow is having the maximum value, then it is the capacity of an ST cut for some cut. Or if you have a flow whose value is same as the capacity of an ST cut, you can conclude that that is the maximum flow. I hope the theorem is clear. Now we can try to prove it. We will first try to prove that if condition 1 is true, then condition 2 must be true. How will you prove it? We are trying to prove it using the method of contradiction. Okay, so assume that F is a max flow, but the second condition is not true. That means there exists an augmenting path in the residual network. Okay, we are assuming the opposite. F is a max flow, but the second condition is not true, meaning there exists an augmenting path. We know from the Ford Fulkerson method that if there exists an augmenting path, right, and then the flow along that augmenting path, which is Fp, can be augmented with the original flow to get a value, to get a flow with a value which is greater than the existing flow value. That means if there exists an augmenting path, then you can increase the flow, which contradicts the fact that the given flow is maximum. Okay, so we can conclude that if F is a maximum flow, then the corresponding residual network does not contain any augmenting path. And now we will try to prove that if the condition 2 is true, then the condition 3 must be true. In this case, we will try to have a constructive proof. We can assume that the condition 2 is true, that is no augmenting path in GF. Then we will try to define an ST cut whose capacity is the value of that flow. We can see that. Assume that condition 2 is true, that is the residual network is not having any augmenting path. Then we can construct an ST cut satisfying this property. We are going to define it like this. Then define an ST cut as follows. What is the ST cut? S is the set of all vertices to which there exists a path from the source in the residual network. Note that there is no augmenting path means T is not reachable from the source vertex. So you are collecting all the vertices to which there is a path from the source vertex, and all other remaining vertices, definitely T is there, forming the set T, and that is clearly an ST cut. We can try to understand with an example. Here is a flow network given with a flow value 23 and the corresponding residual network is here with no augmenting path. So, the condition 2 is true. Then see what we have defined. This is the ST cut we defined. What is the set? Yes, the set of all vertices to which there is a path from the source. To V1 there is a path, to V2 there is a path, to V4 there is a path. And you can see that there is no path reaching into V3 or T. So, this is the set S and the remaining forms the set T. So, definitely an ST cut, and this is how you defined. Now, we can have certain properties on this ST cut. Suppose you take a vertex U from the set S and V from the set T, and suppose that U and V are connected, right? Then what you can say, if there is an edge from U to V, we can conclude that then the flow along that edge is maximum. Maximum means it is the capacity of that conduit. For example, these are the 3 such edges crossing that cut. Okay, 1, 2 and 3. And in this particular example, you can verify that all these flows are maximum. It is utilizing the full capacity on every conduit. And we can prove that in general it is true, because otherwise there must be remaining capacity, that is the capacity minus the flow value. Then the corresponding edge must be there in the residual network, and so we can prove that UV must be an edge in the residual network. Suppose here the flow was 10, then this edge must be there with the capacity 2. Okay, that is what I am telling. And if UV is an edge, where from U is coming? From the set S. Where from V is coming? From the set T is what we assumed. But if UV is an edge, that means from the start vertex you can even reach into V, and therefore V must be in the first set itself, and which is a contradiction. So, what we are telling is that if you take any edge crossing the cut, then it is already having the maximum flow. For example, these 3. Now, the second property, if you take any edge crossing the cut in the reverse direction, that is from this direction, then the flow must be 0. Why is it 0? Because if it is non-zero, that means there is a flow from this set to this set. We must definitely have a reverse set in the residual network with the value same as the flow value, right? So, what will happen? Then we will be having a reverse edge in the residual network, and that will make V an element of S, which is again a contradiction. I hope you are following, otherwise please see it again and verify that what I am telling is correct. So, these are 2 properties. Then the only other condition is for a pair of vertices U, V such that U from the first set and V from the second set. We have considered the case in which there is an edge from U to V, and another case where there is an edge from V to U. Now, the only other case is there is no edge between U and V. Then we know that there is no edge, and hence the capacity and also the flow in both direction must be 0. This is a direct case, because if there is no edge, there cannot be any flow. Now, what is the net value of a flow across the ST cut? Here is how it is defined. The sum of all flows crossing the cut from S to T minus the sum of all the flows coming from T to S. Okay, but here we know that from left to right, if an edge is crossing the cut, the flow value must be same as its capacity. So, this is same as its capacity is what we proved. And here we proved that In the opposite direction, the flow must be 0 when the when the residual network is not having an augmenting path. So this is 0 and this is the capacity of UV is what we proved here. Okay, the flow from left to right is maximum and flow from right to left is 0. So this component is becoming 0 and you are getting the result as the capacity of the maximum capacity or the total capacity of all the contours crossing the cut from S to T, which is nothing but the capacity of ST. So we proved that in the defined ST cut, the net flow is the capacity of the cut, and that is what we wanted to prove. So we proved that if there is no augmenting path in the residual network, then we can have a cut whose capacity is the value of the given flow. Okay. So we proved that 2 implies 3. Now it remains us to prove that if the condition 3 is true, then condition 1 must be true. We can prove it, it is more easy. Recall that corollary that we discussed for that lemma. What is the corollary? We said that the flow for any flow is any network is upward bounded by the capacity of a cut. That is, the net flow value must be less than or equal to the capacity of any ST cut. Now from the condition 3 we know that there exists an ST cut and a flow with the capacity, and hence it follows that F is maximum, because from the corollary we know that the flow value is upper bounded by the capacity of a cut. Now you have a flow with the capacity of the cut as value, so that must be the maximum flow. So we proved that condition 1, if condition 1 is true, then condition 2 must be true, and if condition 2 is true, then condition 3 must be true. This is what we proved, and we also have proved that if the condition 3 is true, then condition 1 must be true. So we proved that they are equivalent. And now see that this is giving you a proof of correctness for the Ford Fulkerson method also, because the Ford Fulkerson method terminates when there is no augmenting path in the residual network, and now this theorem proves that when there is no augmenting path, the current flow is the maximum flow, and thus this gives us a proof of correctness for the Ford Fulkerson algorithm. So we proved this, and with this we are finishing this lecture, and today we have seen the max flow min cut theorem, which gives us a proof of correctness of the Ford Fulkerson algorithm that we discussed in the last 2 lectures. Thank you.